Doppler shift measurements of binary systems. I want to pursue the idea of binary stars. They give us not only the information that we want regarding the orbit, but there is even more that we can get out of it, which is even more exciting. So I will remind you what a binary system looks like. Remember the second exam. I'm sure you will never forget that second exam and maybe never forgive me for that. Binary system, star 1, radius r1, mass m1, velocity v1, and star 2, going about their common center of mass, mass m2, radius r2, and velocity v2. m1 r1 equals m2 r2. That's the way the center of mass is defined. Imagine that you as an observer are somewhere in the plane of this orbit and you are here. And you're observing this system going around. Kepler's third law, which you derived on your exam as well as on an assignment. The period squared equals 4 pi squared times r1 plus r2 to the power 3 divided by g times m1 plus m2. Let me check that to make sure I have that right. Yes, that is correct. Imagine now you can make the Doppler shift measurements of both stars. You make the Doppler shift measurement of star number 1, so you measure lambda 1 prime as a function of time. Out of that pops immediately the period of rotation. Out of that pops the velocity, as we discussed. Out of that pops the radius r1. And now you measure the Doppler shift of star 2 as a function of time. Out of that pops the period, which of course better be the same. Out of that pops its velocity in orbit, and out of it pops its radius. All these things come out of the Doppler shift measurements. But if you know r1 and you know r2, then you also know r1 plus r2. So you know this part in Kepler's third law. Since you also know the period, you can find what m1 plus m2 is. So now you get an extra bonus. You know now what the sum of the mass of the two stars is in the binary system. But you also know that m1 r1 is m2 r2. So now you have two equations. You know what m1 plus m2 is, and you know this equation, and you can solve for m1 and m2, which is an amazing thing when you come to think of it. So we finally end up with the mass of star 1 and the mass of r2. All this comes out of Doppler shift measurements. The velocities, the radii, the periods, and even the masses of these objects. Now, if you as an observer on Earth are not exactly in the plane of the orbit, then the situation is a little bit more complicated, and I will not discuss that here today, because in principle, it doesn't affect the idea behind Doppler shifts, but for astronomers it is very important. It's really a nuisance, but I will not discuss that in any detail. I want to discuss a fascinating application that we have in X-ray astronomy, namely we have X-ray binaries. What is an X-ray binary? Well, it is a binary system. This is a star not unlike our sun, has a certain mass, has a certain radius, and it is in orbit, let's say with a neutron star, even though it could be a black hole. But for now, let's just assume it is a neutron star. And if these two masses are the same, which I only use for the sake of simplicity, in practice they could be very different, then there is a point between these two, right in the middle, whereby the gravitational pull in one direction is the same as the gravitational pull in the other direction. And we call that the inner Lagrangian point. In other words, if you were there, the neutron star would pull at you with exactly the same force as the other star. So you wouldn't know where to go. If this inner Lagrangian point lies below the surface of this star, that means if the stars are a little closer than I have drawn them here, then the matter of this star will fall towards the neutron star, because the pull in this direction is then larger than the pull in this direction. Now, of course, this system is a binary system. They go around in the plane of the blackboard, say, and so this matter cannot fall radially in, but it will fall in and spiral in and forms what we call an accretion disk around the neutron star. This is called the accretor, and this is called the donor. There's mass transfer from the donor to the neutron star. Oops, I just noticed I misspelled the word accretion. There is an R in accretion. And as that occurs, there is a tremendous amount of energy that is released. I want to blow up the neutron star. Very simple 801 considerations now. What comes is extremely pedestrian. This is the mass of the neutron star. And this is the radius of the neutron star. And I take a little bit of matter, m, and I drop it from a large distance onto the neutron star. At what speed will that little piece of matter reach the neutron star? You should almost be able to close your eyes and give me that answer right now. The kinetic energy, when it reaches the neutron star, equals 1/2 m v squared. That is the speed at which it will crash onto the neutron star. And that must be m neutron star g divided by the radius of the neutron star. You always lose your m, and so you'll find that the speed at which it reaches the neutron star is the square root of 2 m neutron star times g divided by r neutron star. You should remember this equation. This was the equation that we had for escape velocity. If you are here and you go back to infinity, you need exactly that speed. So if you fall in from infinity, that is exactly the speed at which you reach the neutron star. It should obviously be the same number. And you don't really have to be infinitely far away. You just have to be much further away than the radius of the neutron star. When this matter crashes onto the neutron star, the kinetic energy that is released is 1/2 mv squared. It is converted to heat. And to give you some feeling for the incredible power of a neutron star, if you make this little m as little as 10 grams, think of it as a pretty full-size marshmallow, and you throw a marshmallow from a large distance onto a neutron star, the energy that is released is comparable to the atomic bomb that was used on Hiroshima. A 10-gram object thrown onto a neutron star. The reason being that this velocity becomes enormously high. If you put in for the neutron star a mass of about 3 times 10 to the 30 kilograms, and you take for the radius of the neutron star about 10 kilometers, you will find that that velocity becomes about 2 times 10 to the 8 meters per second, which is about 70% of the speed of light. And because of this enormous speed, 1/2 mv squared is horrendously high. It is a conversion of gravitational potential energy to kinetic energy, and then ultimately to heat. Now, nature is transferring mass at an extraordinarily high rate in many of these binary systems. There are several hundreds in our own galaxy. The mass transfer rate, which I call the MDT, so that is the transfer rate from the donor onto the neutron star, that transfer rate is roughly 10 to the 14 kilograms per second. There's a horrendous mass transfer rate. You can calculate by multiplying it with 1/2 v squared how many joules per second are released in the form of kinetic energy. That means in the form of heat. And I call that the power of that neutron star. And that then, for this mass transfer rate, that's about 2 times 10 to the 30 joules per second, which is watts. And that is about 5,000 times larger than the power of our own sun. But the temperature of this neutron star, because of this enormous amount of energy release, the temperature would reach values of about 10 million degrees Kelvin. And at that high temperature, the neutron star would emit almost exclusively X-rays. You and I are very cold bodies, only 300 degrees Kelvin. We radiate electromagnetic radiation in the infrared part of the spectrum. We have warm bodies. When you hold someone in your arms, you can feel that. If I would heat you up to 3,000 degrees Kelvin, you would become red hot. And we could turn the light off and I would see you. You're just emitting red light. If I would heat you up to 3 million degrees, you would start to begin to radiate in X-rays. You may not like it, but that's a detail, of course. So I want you to appreciate the fact that the kind of radiation that you get depends strongly on the temperature, and at 10 million degrees, you're dealing almost exclusively with X-rays. So these binary systems are very potent sources of X-rays. The neutron stars rotate around. We discussed that earlier, conservation of angular momentum. And they have strong magnetic fields. The matter that falls onto the neutron star already heats up during the infall, because there is gravitational potential energy released. And so the matter is so hot that in general it's highly ionized. And highly ionized material cannot reach a magnetic neutron star in all locations that it prefers to do so. In 802 you will learn why that's the case. However, the matter can reach the neutron star at the magnetic poles. And so what you're going to see now is you're going to have a neutron star with magnetic poles. So the matter streams in onto the magnetic poles, which give you two hot spots. And if the axis of rotation doesn't coincide with the line through the two hot spots, if the neutron star rotates, you're going to see X-ray pulsations. When the hot spot is here, you will see X-rays, and when the hot spot is here, you will not see X-rays. And so we observe from these systems X-ray pulsations. Now, think of the following. The X-ray pulsations are a clock. It is the clock of the rotating neutron star. If the neutron star in a binary system, because they always are in a binary system, these X-ray binaries, if it's coming to you, you see Doppler shifts. The ticks of the clock come a little closer together. If the neutron star moves away from you, the ticks of the clocks are a little bit further apart. That is exactly what Doppler shift is all about. So by timing the pulses of the X-rays, you can get a handle on the Doppler shift of the neutron star. That means you can get the speed of the neutron star, you can get the radius of the orbit, and you can get the period, just like we discussed before. But now you take an optical, the X-ray observations, by the way, have to be made from outside the Earth's atmosphere, because X-rays are absorbed by the Earth's atmosphere. Now you take an optical telescope and you look from the ground, and now you see the optical spectrum of the donor. And what do you see in the donor? You see these absorption lines. And as the donor moves around the center of mass, these absorption lines move back and forth. The Doppler shift of the donor. So you know the velocity of the donor, you know the radius of the orbit, and you know the period. So now you have a situation that I just described earlier, that you have the Doppler shift of both objects. And remember, I told you that you also get the masses. You get the mass of the donor and the mass of the accretor. Before I go ahead, let me show you some slides. So we have to lower this again, if that's possible. Yeah. I want to show you an artist's conception of such a binary system. So this is what it may look like. You see the donor there, and you see the neutron star right here, so small, of course, that it's invisible, and this is the accretion disk. Swirls in the matter, ends up on the neutron star. And this is another view that gives you an idea of the donor, and then the swirl of matter, and then it swirls in and ends up here on the neutron star. And here, you see data that were obtained in 1971. It's clear evidence for the existence of these rotating neutron stars with these X-ray hotspots. You see here the observed X-ray intensity as a function of time. And the actual data are these very thin lines. and this bold line was drawn over by the authors to convince you that you see a signal which is highly periodic. The time from here to here is 1.24 seconds. This object was called Hercules X1. So this is one of the magnetic poles, and this is the other magnetic pole. One magnetic pole and the other magnetic pole. So you see here unmistakably the rotation of the neutron star and the X-ray pulsations. Here you see data from the same object, but now the time scale is very different. From here to here, this is 2 days. And when you look at this data alone, forget this for now, notice that you see the source is active in X-rays. The 1.42 second oscillations you cannot see, of course, anymore because the time scale is different. But notice here, there are no X-rays at all. 1.7 days later, no X-rays at all. 1.7 days later, no X-rays at all. And so what you're looking at here are what we call X-ray eclipses. When the neutron star moves behind the donor star, all the X-rays are absorbed by the donor star, and you get X-ray eclipses. In other words, you get, independently from the Doppler shift, you also get the period of the orbit by the X-ray eclipses. And this really changed our whole concept of astronomy, the existence of these neutron star binaries. And now comes a part, what are the masses of these objects? I already alluded you to the idea of the possibility that there may be black holes. All the mass measurements that have been done to date of these neutron stars, where you see the pulsations, all of them are very close to 1.4 solar mass. And there's a good reason for that. That's not an accident. In 1930, the physicist Chandrasekhar predicted that white dwarfs could not exist if their mass is larger than 1.4 solar mass. It was a quantum mechanical calculation for which he received in 1983 the Nobel Prize. Remember, we discussed white dwarfs earlier. A white dwarf has about a radius of 10,000 kilometers, about the same as the Earth. And imagine that you have a white dwarf, and you add matter to the white dwarf, and you pass the 1.4 solar mass mark, then the white dwarf will collapse and becomes a neutron star. And so when we measure the masses of neutron stars, it turns out, maybe somewhat by surprise, that they're all very close to 1.4. If you could add more matter to the neutron star by accreting more and more matter, and you reach the point that the neutron star becomes as massive as 3 times the mass of the sun, we believe that the neutron star can no longer support itself and becomes a black hole.